Okay, yeah, so my talk will be contain three parts. So in the first part, I'm going to give you a very quick summary, a one-page summary of polynomial operation and moment estimates hierarchy. And then I'll go into two topics, where the first topic is about using that for perception and then using that for plan. Okay, going to the first part. So polynomial operation is a family of mathematical operation problems where our goal is to minimize a polynomial objective f of x over a set K that is also defined by polynomial equalities and inequalities. So this problem in general is non-convex, as you can see in the picture here. So the moment SOS hierarchy, so is a convex relaxation hierarchy that relaxes this POP into a sequence of convex semi-definite programs written in here. So in this convex SCP, the distinct variable x is a collection of matrices and matrices where each of the matrix is positive semi-definite, and then they have to satisfy certain collectively linear constraints ax equal to b. And this actually is a convex program as shown in here. So the nice property of this moment SOS hierarchy indexed by this relaxation order kappa, which is integer here, is that as this kappa increases, you get a non-decreasing sequence of lower bounds that converge to the optimal f star from below. Right? And then therefore, if you have some local minimizer or a feasible point of the original pop, then by combining the lower bound and the upper bound, you can compute what we call a relative subalternative gap that can potentially satisfy the global optimality of the solution or quantify the subalternity if the solution is indeed suboptimal. Okay, so this is the toolbox here. So when you see a very powerful tool like this, you have to always be very conscious about the price of this tool. So the underlying price of this moment SOS hierarchy is that you can end up generating a convex program that's extremely large. So this is the diagram of the SCP where you have this two types of matrices. The blue one is what we call moment matrix, and then the smaller ones are what we call localizing matrices. And the size of this moment matrix, which is the big matrix in this block diagram, is SD by SD kappa by SD kappa, where this SD kappa is a binomial D plus kappa choose kappa. And then the number of linear constraints, which is the number of connections, or the black line you see here in this SCP, is roughly SD2 kappa. So then you can do some simple calculations. If I'm solving an original pop, which has 100 variables, then you have a matrix that's roughly 5,000 by 5,000, and then you have a number of constraints, maybe a few million. But then when you have a pop of 1,000 dimension, then you have a matrix that is about 500,000 by 500,000, and then the number of linear constraints can be 10 to the power of 10. So this is really the price you need to pay if you have to use this framework. And this is for the relaxation order kappa, which is some examples I will talk about later. So in our group, we really our goal is to how to solve these SCPs faster and faster. And then we work on two directions. Where in one direction we're working on the theory. In there we're trying to investigate the dynamics and geometry of these of some first order methods. Unfortunately for today, I'm not going to talk about that. So I gave a talk somewhere else last week, and I uploaded slides to this Google Drive. If you're interested, you can take a look. But today I want to talk about the practice side, which is how to combine this framework using the structures in problems, structures of robotics problems. Okay, so with this, I'm going to go to the second part, which is using this hierarchy for robot perception problems. So the problem I'm going to focus on here is this problem called structure from motion or functional adjustment. So the problem here is you are given a sequence of images observing certain environments, and the goal is to reconstruct the poses of the cameras as well as the 3D structure. So the way this problem is solved is that we can first create what we call a view graph, where in this view graph we have two types of nodes. The red ones are the camera poses, and the blue ones are the 3D landmarks we're trying to recover. So the measurements we have are measurements connecting points to poses. So the measurements on the edges are the 2D key points that we measure and generate from certain feature matches using computer vision techniques. And then to solve this, to recover the variables on the nodes from using the measurements from the edges, we're going to solve some nonlinear optimization problem, actually some nonlinear dispersed problem, where our decision variables are the points and poses, and our objective function is to minimize the reprojection error along every edge of this graph. And then this, there has been lots of solvers for this type of bundle adjustment problems. For example, COMAP series, GTSAM, some of these covered in this series of talks in the workshop. But many of these techniques, as you know, that they are local solvers. Therefore, most of them you have to give them some initialization, or and most of them also, for example, the COMAP solver is also slow because they have to stabilize this this algorithm using by incremental updates. So the key challenge, as in this bundle adjustment problem, is really this perspective camera model, where you have a point in 3D getting projected in 2D. Therefore, you really lose a dimension in the measurement, and then you have to formulate this rational function using the first two coordinates divided by the depth. So the idea that we had is that now that we have very good foundation models which can give you sort of zero-shot depth prediction, we're going to transform the measurement that was originally 2D using some sort of lifting technique from the depths. So we're going to generate some pseudo 3D points by multiplying the original bearing vector with the depth predicted by the monocular depth prediction models. This then gives you what we call a scaled bundle adjustment problem, where now you not only need to optimize the points and the poses, but also need to optimize certain scaling factor per image to correct the potential mistakes of these foundation models. And then, but really the nice thing here is that you were able to get rid of the rational function in the objective by replacing them with these 3D difference measures directly in the objective function. So this now is a polynomial optimization problem, right? Because everything here is polynomial. So then you do some mathematical massage, and then you can use the moment SOS relaxation. In this case, just the first order, kappa equal to 1. You can get a semi-definite program that looks like this, where the objective, where the decision variable x here is symmetric matrices satisfying the constraint that the diagonal blocks have to be scaled identity matrices. So if you indeed formulate this problem and solve it, you get the very nice empirical observation that these relaxation is empirically tight, in the sense that you can certify the rank of these matrix optimal solutions are equal to 3, and therefore you close the lower bound and upper bound. However, we want to solve really large problems. Therefore, for example, when the number of images is over 2,000, then commercial solvers like Mosaic will have some trouble solving them. So the idea here then is to use this famous technique by Buehler and Montero, which is to factorize these convex SDP into, again, a nonlinear optimization problem by factorizing the symmetric matrix using a low-rank factorization. So this is a little bit counterintuitive, right? Because we started with a non-convex problem, and then we relaxed it into a convex problem. Now we're saying that we want to go back to the non-convex optimization land. This is potentially a very bad thing to do. So the good thing here is you can come up with this Riemannian staircase algorithm where you start with a very low rank factorization, for example, r equal to 3. Then two things will happen. Either you can merge the optimal solution at a lower rank, or you can certify the solution is suboptimal, and actually you can do a descent in the higher rank space, and therefore converge to a better solution. So this is actually still certifiably globally optimal, and empirically the good news is we don't need to go very high rank. And then we did some extra work of putting this algorithm into the CUDA GPUs there, so that you can parallelize these second order trust region algorithms on GPUs. And then this is some results that we get using this method. So here we have the classical building Rome in a day data set, where we have 4 data sets with increasing sizes. And then the first observation here is that if you use the classical BA solvers without the learned depths, then because these solvers are sensitive to the initialization, therefore they only work when you have a good initialization. And then the MANOP here is our algorithm just implemented using the MATLAB MANOP package. So this basically runs in CPUs in your MATLAB. So this, it's already, although it can merge the optimal solution, therefore verifying the correctness of the theory, but it's quite slow. But if you compare with our solver, which is XM here, which is implemented in CUDA, then it's really very fast and scalable, and also gives you very accurate estimations. And then this is some of the reconstructions you can see from the BAL data set, where the red are the cameras and the blue are the points. And this is another, I think this maybe somewhere in UK. And then this is some indoor data set. Again, here are 4 data sets with increasing sizes. This is a de facto COMAP approach. Again, it's very robust because it's doing incremental bundle adjustment but very slow. And GlowMap is a new approach from the vision community last year. It's much faster, but still it can take hours. And hours, is can reconstruct 2000 frames usually in around 10 seconds. Okay, and then these again some of the results from the replica data set. This is some MIPNERV and ZipNERV data sets with neural rendering. And then this is some TUM and IMC data sets. So the nice thing to see here is that these depth separation models actually not trained on these data sets. So therefore, it's really you can use up the zero trust generalization of these methods of these foundation models with convex population. And this is a private data set with about 20,000 images. Here I'm only showing the cameras. So recently, we're trying to move, kind of generalize this 3D reconstruction to 4D reconstruction because our robot always faces dynamic environments. So in these 4 videos, what you can see, you are seeing a sequence of images, and the camera is also moving. There are also some dynamic objects in the scene. So our goal is to reconstruct the camera poses, as well as the parts of the static scene, as well as dynamic objects, and potentially can do neural rendering using, for example, 3D Gaussians. So this is some results that we get. This is purely using convex population, followed by some Gaussian rendering. So as you can see, the static part still follows the XM approach, but what we added here to accommodate the dynamic objects is something we call the embedded deformation graphs. So basically, with these robots, you see that because they are moving, you have this kind of wireframe, but they are deformable, and then you can reconstruct these wireframes using convex population exactly in the same way as we did, using a QCQP followed by a low-rank pure material. And then you can do dynamic Gaussian rendering style things. Okay, then I'm going to go to a bit about motion planning. So the motion planning problem here that we're going to focus is trajectory planning or trajectory calculation. So in this formulation, we're optimizing a sequence of states and controls, where the xk is a state, uk is a control, fk here is the dynamics, and lk here is the cost. We added this lambda k here is what we call a contact variable to accommodate contact-rich motion planning problems. These can really instantiate in 2 ways. One is to have discrete modes, or you can have contact implicit formulation. This will give you orthogonal constraints. And the ck here are some path constraints. We're going to assume that this is a polynomial population problem. So if you do some simple math, if you do a trajectory planning with horizon equal to 50, and maybe the dimension of the states and controls are maybe 20-ish, then you get a polynomial population with about 1,000 variables, right? So therefore, based on the simple math I did, you're going to get a trillion variable SCP, if you don't exploit any additional structures. So the nice thing about the trajectory planning problem is that this problem has this natural sparsity from the Markovian property of the dynamics. Specifically, if you write down this problem using the factor graph representation, where the blue nodes are the variables, and the red ones are the functions or costs containing these variables, then you naturally see sort of a graph representation of this problem, where you can group these blue nodes into cliques, right? Where every clique contains only the variables at this time step and the state at the next time step. And then these cliques, if you look at the clique as a single node, then these cliques form a line graph. So this is really the sparsity of the problem comes from Markovian. And then this sparsity then allows you to sort of formulate a much scalable moment SOS hierarchy at kappa equal to 2, where the basic idea is, I used to have a very gigantic positive Semidefinite variable. Now I can, break it into many smaller positive Semidefinite variables. Therefore, you have this sparse SCP where the matrices are assembled in a line, and then the constraints are between these cliques as well. So then, you have this very sparse formulation where the cones are getting smaller. You can think about using first-order methods such as ADMM to solve this, and you can use GPUs to parallelize certain aspects of this problem. I'm not going to talk about the details here, but this is some, this gives you some advantages. So then we apply this first to some contact-free trajectory calculation problems, where here, for example, is the simple carpal problem, where the dimension of the states and controls are very low. Therefore, you can see that in many of the, in almost all initial conditions, you can reliably swing up the car pole, obtaining the global optimal solutions. And then this is the car backing problem, where you have to back up the car to the garage while avoiding some of the constraints. And then this is a little bit like toyish rocket landing or satellite landing problem. And then, then we thought about applying this to contact-rich problems and also maybe to a broader family of polynomial application problems with, sparse. Then we really started, cooking this sparse polynomial application toolbox, which we call SPOT. So then the idea here is really, to allow practitioners to use this framework with lower barrier. So if you give me a POP, written as as a symbolic program where you define your variables x and then define these polynomials, I want to have a parser that parse these POP and then give you the STP so that you can pass it to semi-definite programming solvers. So the idea here is, this can be unified in some sort of graph approach. After I get your POP, I can establish this variable level sparsity graph. And then from this graph, I can do Coro extension and generate the maximal cliques. And then I can also do the term level maximal clique. So here, this the typo. So this should be, actually, this is not a typo. Yeah. So I can get the variable level maximal cliques. And then I'm going to formulate the term level sparsity graph. And then I'm going to get the term level maximal cliques. So what this generates is so the first level, the variable sparsity graph will give you a sparse STP that looks like this, and then the term level sparsity graph will further break these large PSD phone constraints into smaller ones. So you end up having many, even thousands or tens of thousands PSD phones, but every cone is potentially smaller. So this is fully automatic, right? And then you can also, as a practitioner, if you have certain domain expertise and you want to try out your own sparsity patterns, you could also do a semi-automatic way where you parse some of your own sparsity by assigning or grouping variables together and asking the parser to parse it for you. Okay, and then this is implemented in C++, with bindings to Python and MATLAB. And then, we recently, tried to work this a little bit above beyond robotics. And so this is some of the natural gas network operation and problems where we get, this from some of the gaslit test data. So the idea here is, when you have a natural gas network, you want to, some attackers is going to break some of the pipes, and you want to solve certain polynomial operation problem where you want to, investigate, what is the minimum demand that can still be met on the surviving network. So this gives you polynomial operation problem, and this is, SPOT applying to this type of problems. In the left, you see a relatively small scale problem where I think you have about 500 decision variables. But if you look at the clique size, the maximum clique size, the clique with the maximum number of variables is actually 8, right? Which means that the problem is extremely sparse. And some of the sparsity actually is inherited from the sparsity of the original graph defining the natural gas pipeline. And then on the right-hand side, you see a top with about I think at 1,000 or maybe a bit over that. And then you see that these red ones are circles that contains maximal cliques. So just to show you that these framework can solve POPs beyond robotics. Now I'm going to show you some contact-rich planning. Here's the push box, where you're trying to push the box to align with the target position. And then this is the push T, where you push the P block. And then this is some planar Heng and push block through the tunnel. And this is some real-world implementation where you deploy this in Franca Panda. You have the T block. You see that this, and we're doing this in MPC fashion so that you resolve at every time step. And you can see that for this T without any obstacles, this works very well. And then the power of MPC is that if you disturb the dynamics of the system, the nominal robustness of MPC still gives you a good result. For example, here you can, I think the one I like the best is the bottom left, where you tie up this T with the cable. Then the contact is really shifting between the points on the page, right? And you see that eventually it will still be able to push that into the target position. Okay. The last thing I want to talk about is some work that we're recently doing, which is exploring partial timings. So many of these, so the trade-off you have to cope with eventually with moment SOS hierarchy is that you have to admit that the kappa equal to 2 is perhaps the biggest scale problem that we can solve in the near future. But then, even when you apply kappa equal to 2, when you solve the SCP, you'll realize that many cases the SCPs is not fully tight. You get a duality gap that's maybe 5%, 2%. But then there's some intriguing things happening in these cliques if you look a bit closer into what we call partial tightness. Is that we find that the tightness across these cliques are actually non-uniform, in the sense that some of the cliques are tighter than the others. And interestingly, in trajectorization, the first clique, which means that the control at the first time step, is almost always the first clique that gets tight. So then, if let's say the first clique is tight, then you can recover, global optimal solutions. In this, this is not very accurate, but if it's tight, then you can recover flat extension solutions from this. And then you can, freeze the variables, right? You can eliminate the variables from the tight cliques. And then you can resolve this, right? Because now, you can, this is a heuristic, right? We want to prove that this is actually the global optimal solution, right? Because this is a little bit unusual, right? Because we're sort of doing a blockwise, operation here, where we optimize certain coordinates first, and then, gradually eliminate certain cliques, and then redo this, right? But in many examples that we find that if you do this, then this is actually very strong in the sense that the bluish line. So this example is that you have a Dubin's car example, and then you want to do a trajectory elimination problem from the bottom left to the top right. So if you do a second order relaxation, like this one of the curves is the second order relaxation. You see that the operation, the solution is not tight, therefore you don't get very good trajectories. In this case, even if you increase the relaxation order to order 3, which means that now I'm solving a larger scale problem, this is still not tight. However, the interesting thing, if you solve the first operation problem and then freeze the first action and then resolve it, then you get this beautiful trajectory that is collision free and also goes to the goal condition, right? So this is what we call partial tightness. Our conjecture is that if you do things like this, it's sort of like dynamic programming, and then you have some sort of self-evidence of the tightness of the every clique, so that the projection of certain coordinate of the variable into certain coordinates is tight before the others gets tight. Okay, stay tuned for those results. So finally, this is a summary. So the moment SOS hierarchy, which I don't give a lot of details, is general machinery for solving POPs using SDPs. It's very powerful, but you have to be careful to not abuse it because it's very expensive. And then I'll talk about using some problem structures in robotics that you can solve the scale this to medium scale or large scale problems. In perception, we use the low rank solutions plus GPU acceleration, and in motion planning, we use the sparsity and also GPU acceleration. With that, I want to thank the students and also the funding. And I can take some questions.